Welcome to the lecture series in computer science. As a part of this series, this is a course on artificial intelligence, and in this course today we will be doing the last type of search called the adversarial search. This is in unit 2 and this is otherwise called as a game search. The topics that we will cover today is the minimax algorithm and the alpha beta pruning, the two basic algorithms towards that. So, this is otherwise called as a game search, which I said before. Imagine there is the two players who are playing a chess here on the right side. Okay. So, here the idea of this game is to win, the person ultimately should win. Each of the players assume that that player should win. So, this is basically the assumption that one person should be winning the game, or in other words one player's winning is the other player's loss. The other player who is winning should say the opponent say his opponent should, there should be a loss, okay. Or otherwise it is called as a zero sum game, where there is at one point there is a profit and the other point it is a loss, both are going to match and it is a 0. So, if player A has a maximum value, the player B is going to oppose that and be it at the minimum side. So, this is otherwise called as a two players game. So, the search goes like this. Suppose a player is red, the two players are indicated as a square and a circle here, where the rectangle or the square, this we are going to have a maximum value, and the circle we are going to have a minimum value. The maximum is indicated as player A and the minimum as player B, and how it happens is first player A plays the game, then player B is playing the game, then player A is playing the game. So, this two player game is carried out in this way. Now, this tree is called a heuristic tree. The idea is at this point the player A is at, assume that the player A is at this position at the root. Now, at this point when the tree is getting extracted, we have some heuristic value at the leaves. These the 7, 3 are going to be the heuristic value. The idea behind this tree is at A, at the root side, can the maximum value be 50? Can the player A get 50? This is this point. Can he reach towards this value? In other words, can he win? Or in the worst case, what is the value that A would take? Is it going to be 7, or is it going to be 3, or is it going to be minus 8, or is it going to be 50? So, this is a kind of a tree that if it unfolds and gets some heuristic value down the leaves, player A can manipulate and go in that particular direction, so that he could get some point in the game. So, that he could get some maximum value in the game. He may not be winning, but at least he could estimate the value that he would get. So, that is the idea behind this minimax algorithm. So, let us see at this point, considering the 4 leaves here, take these 2 leaves, which is 7 and 3. This is going to be player B and this is going to be player A. At this point, player B always wants to minimize the value. So, with 7 and 3, the minimum value is going to be 3. Now, when we consider these two values minus 8 and 50, the minimum value is going to be minus 8. The maximum value is player A. Player A wants to maximize and player B wants to minimize. So, player A, when it considers these two values 3 and minus 8, he wants to maximum. So, it is going to be 3. So, the path that player A is going to choose is right here and this direction, where he would get only 3 value of 3, and can he get 50? The answer is no. In the worst case, again why is it called adversarial? At the adverse case, in the worst case, he is going to get only 3 and not 50. Suppose if player B makes a mistake. Assume that player B is making a mistake. Suppose instead of -8, he instead gives 50. This in this case, when B makes a mistake, then player A can get 50. So, in the adverse case, if he is not making a mistake, the value that he can get is only 3. So, this is the essence of the minimax algorithm. Again, the idea is, once we have the heuristic value at the leaves, player A or any player at the root can choose the path with this algorithm such that the adverse effect of whatever value he could get, the practical value that he could get. Now, the performance of this type of search, is it going to be complete if it is a solution and if the finite state it is available? And what is happened to the time? It is going to be order of b power d, which is very similar to BFS, where b is the breadth factor and d is the depth. The space is going to be order of b multiplied by d. The why? The reason is we have to store only this part of the tree. So, the space is going to be b multiplied by d, and if the both players play optimally, then we can say this type of search is optimal. So, that is pretty much the essence behind the minimax algorithm. The next algorithm is alpha beta pruning. Again, if we take this simple search tree, this is a very simple search tree. Assume that we have number of nodes here, the depth may be more than 1000. So, here I have kept only 1 or 2, the height is going to be 2. Suppose we have 10 or 15, then we have to go through at each level and the time and space complexity will increase. And if you see even the tree, the path that it goes through, it will increase. So, is there a way to cut short that path? At the same time, can we get some values? So, the answer is yes, and it can be done through alpha beta pruning, through which we can prune off is cutting off certain part of the tree, so that we need not go through the entire part, but at the same time we will be able to get the result. Okay. So, the first I will describe the algorithm, then we will work out 1 or 2 examples. So, here in alpha beta pruning we are going to have 2 variables, one is called alpha, another one is beta. Alpha is always going to be associated with max nodes. Max node, remember we had an example with a square or a rectangular node. At initial point, alpha is a variable and we have the variable to be -infinity. Beta is going to be the lowest value choice at, and it is associated with the minimum node, and here in the last example we represented this as a circle. At start, beta is equal to +infinity. Initially alpha is -infinity and beta is +infinity. Now, the algorithm goes like this: pass the current values of alpha and beta to child nodes during search. Suppose you have a search like this, and alpha and beta nodes, whatever the values are, we are going to just pass it here. But when we are going to pass the values in the reverse direction or in that direction, we are going to update the values of alpha and beta such that max node update alpha and min nodes update beta at min nodes. These two are very much essential. We will do an example, then this statement will be clear. Then we will do this repeatedly. This step will be done repeatedly until when alpha is greater than or equal to beta. Okay, we will do 2 examples here. Suppose we take an example here, okay, and everything goes through the depth first search. Okay. Right here I have written some numbers here, and these are the heuristic value, meaning 8, 5, 2, 9, 4, 1, 2 and 3. Okay. These are some heuristic value. The idea is, at this point this is player A, mapping it to player A, and this is player B, this is player A and again player B. this is max node, min node, this is max node and circle is min node for us. This is again is max node and this is again is min node. For this example, we are going to apply alpha beta pruning. Again I am going through this algorithm and then we will do. So, at each node we are going to have alpha is equal to minus infinity and beta equal to plus infinity. So, here at each of the nodes I am going to write alpha as minus infinity and beta as infinity. Similarly, the second node, this is the initial start point for all the nodes. And here also, here alpha is minus infinity and beta is infinity, and here alpha is minus infinity and beta is infinity, and here is alpha is minus infinity and beta is infinity for all the nodes. Now, always from the algorithm, max update, at max node update alpha, at min node update beta. These two are going to be essential. Okay. Now, assume that this is a search tree, a simple search tree, and we are going to have a depth first search. A depth first search goes in this fashion. From here, this is player A, he goes through this route and here finds out 8. Now, this 8 we are going to backtrack and this is a max node. At max node we are going to update alpha. This is maximum of this 8. This is going to be max of 8 comma minus infinity. This is going to be 8. So, this value becomes 8, comes down, this is 5, goes up, again alpha maximum of 8 comma 5 is 8. So, this value goes up 8. Now, this is a min node. At min node we are going to update beta. So, this beta is going to be 8. Now, comes down, here beta is alpha is minus infinity, beta is 8, beta is 8, comes down, this is 2 and here it is going to be 2 and here it is going to be 9. When it comes, it is going to be 8, and since 9 is greater than this number, we are going to prune off. This part will be pruned. Now, it goes up, this is going to be 8, this 8 will come up. So, at this point max updates alpha. So, alpha is going to be 8 comma infinity. So, this value will come down. So, this is 8 comma infinity, so it comes 8 comma infinity. Now, it goes again depth first search. At this point it finds 4, this 4 it gets updated here in the max node, it is 8 comma 4, it is 8 and it is 1 comma this goes, this is 8. And at this point if you see 8 is greater than or equal to 8, in the algorithm it should be alpha is greater than or equal to beta. So, this 8 will always be equal to 8. So, we can prune this part of the tree, which means in the search I need to consider only this part of this tree. This part is not be considered, all these effects, this part need not be counted. You can put whatever numbers here, even 8, 9, 10, 100, this search it will not have any effect going through this path. It will have only the maximum effect will be only from this path. So, this is called as an alpha beta pruning. Again the essence is why we are doing is we can reduce the search space as well as the time by pruning off this tree. This part of the tree can be cut off, so that the entire time will not be wasted by going through that path. So, this is the essence of first example. Let us go through the second example, and the second example is from our book itself. So, assume that this is a max node, this is a max we have given, and this is a min node, and we have some heuristic value which is 3, 12 and 8. Now, with these 3 values, max algorithm will get the minimum value of 3 here, and at this point when it goes back, it will always be greater than or equal to 3. It cannot be, this path will not be the other way around. Now, in the next level, this is a min node where at each point I said initially it is going to be alpha is minus infinity and beta is infinity. Now, in the minimum node, minimum of 3 and infinity, it takes us 3, minimum updates beta. So, this 3 will be the value for this node. Now, in the next stage, minus infinity and 3, this will go here and this will check for 12. Again, between minimum of 3 and 12, it is going to be 3, and between minimum of 3 and 8, again it is going to be 3, and this 3 value is going to go back here, and this will go to the root node. At this node, this is a max node. At max node, alpha is going to get updated, which is going to be maximum of 3 comma minus infinity. Remember, initially alpha is minus infinity and beta is infinity. At max node, it is going to be maximum of minus infinity comma 3. Therefore, this value gets 3 and plus infinity here. Now, it will pass through the next stage 3 comma plus infinity, and when it goes through the depth first search, the other at the heuristic value it finds is 2, and this 2 will again go back in this direction, and in this minimum node beta gets updated because minimum of 2 comma infinity. So, this value will be 2, and if you see 3 is greater than or equal to beta, when alpha is greater than or equal to beta, it is going to prune off. Therefore, whatever the values are going to be right here, even if it is going to be 100 or 200 or less than that, because of this value, this part of the tree gets pruned, and this value is again going back, this value, this 2 is again returned back, because this is the minimum value, this is returned back here, and 3 and this alpha and beta value, this is passed to the kids, to this child with the same value, alpha and plus infinity is passed to this value, and when it goes to the depth first search, again at this heuristic value it finds as 14. So, now alpha is 3 and beta is 14, alpha is less than beta. So, nothing will happen and it will get 5, and this beta will get updated, this is minimum of 14 comma 5. So, this will get updated, and then 2 and 2 will get updated here, because the minimum of 14, 5 and 2 is 2. So, this 2 will get updated and it is returned back to that value. So, this is the essence of minimax algorithm, where we are seeing the part of the tree is getting pruned. So, for this example, this part of the tree is pruned. Okay. So, for this session, this is a question that we can have, where you have the heuristic value of 3, 4, 1, 2, 7, 8 and 5, 6. So, and which nodes can be pruned for this example. And to start with, this is going to be max node, and this is a example from Russell and Norvig. This is a min node and this is a max node. Okay. So, how you can do is start with alpha is equal to minus infinity and beta is equal to infinity, and for all the nodes, first we have to have the initial value. I will give a few start with the example here, and you can finish off this question later. So, really here alpha is minus infinity and beta is infinity. Suppose through depth first search it comes like this, and it finds 3 as a value, and because if it is a max level, alpha gets updated to 3 and it comes down this 4. So, alpha gets updated to 4 and this 4 will pass through, and at this stage this is beta, this beta will get updated to 4, it will come back and it will see this is 1 and this is alpha, this 1 gets updated here and this 1 is say 2 is greater than 1. So, maximum value is 2, this will get updated 1 and this again will go back, this 4 and this 4 will continue and you can proceed it and see, and in the next class please complete it and we will see which part of the tree is pruned for this question. So, there are 3 examples given in the textbook for you to practice, and this is one of the important AI part or algorithms that is being used prevalently. In this session, we have seen the adversarial search and it helps to make the optimal decisions in a competitive environment, pretty much very specific to that for 2 player games, games like chess or a tic-tac-toe, where they have the opposing goals. The foundation here is the minimax algorithm, where the assumption is one player is trying to maximize the value and the other player is going to minimize the value. And towards the computational part of it, we have seen one of the important algorithms called the minimax or the alpha beta pruning type combined with the minimax algorithm, where the alpha beta pruning prunes off or cuts off certain part of the tree in order to have a computing efficiency in terms of space as well as in time. So, in the next session we will see some performance measures on the minimax and the alpha beta pruning, like we have seen in this minimax algorithm some performance measure, but how is it going to be in effect quantitatively with respect to alpha beta pruning. So, that we will see in the next class, and also with this we are coming to the end of the search, all the search techniques. So, in the next module or next session I will cover an overview of the entire search techniques, starting from uninformed search, from breadth first search, depth first search and the other informed search like greedy best first and A star search, and also the constraint satisfaction problem and the game search. So, these search techniques with the overview and other answers to those problems, some of the problems I have not discussed. So, the answers to that questions also I will discuss in the next session.